Well, hello all. Today we're going to be talking about something called KC. Now there's a nice unisex name for you, KC, the name of modern day girls and boys, Casey. But we're going to be talking about KC in reference to chemistry, or the equilibrium constant. Now we, in a previous video, took a bottle of soda water or soda streamed water and we pumped it full of CO2 gas. Now watch what happens when we release the pressure. Just see if you can see any bubbles. Let's just clear that. Let's see if any bubbles form. Like there, we're beginning to see, and on the side. So it takes a while before you can see bubbles, but now we're seeing a few bubbles coming off. So that was our introduction. Now, what is Kc, or this equilibrium constant? We are looking at Study and Master, page 210 of the grade 12 textbook. Study and Master, 210 page. Okay, let's read what the equilibrium constant is. We have looked at systems in equilibrium, such as, for example, this bottle is a system in equilibrium. It's a closed system. Which factors control shifts in the position of the equilibrium? The ratio of the products of the product concentrations to the product of the reactant concentration, there's a tongue twister for you, is constant for a specific reaction at a given temperature. This ratio is called the equilibrium constant, or Kc. The subscript C refers to the concentration. Whew! I think we just need to have a look at this reaction. We've got A amount, that's the coefficient of substance A, plus B moles of B goes to form reversibly. It has to be a reversible reaction case. C amount, C moles of C, and D moles of D. So A and B are the reactants, that's why they're on the left side of those arrows, and C and D are the products. And A, B, C, and D are the coefficients or balancing numbers. The equilibrium constant of this expression is, now just have a look at this, it's a ratio. We put products C and D over reactants A and B. And the ratio of products to reactants gives us Kc. That's it in the simplicity. But just to make it clear, when you see a square bracket around something, it means the molar concentration. So there is the coefficient. There were C moles of C and D moles of D. And we raise the D to the power of its coefficient, the C to the power of its coefficient, the A to the power of its coefficient, and the B to the power of its coefficient. And then we're multiplying. There should be a dot or a multiply sign. It's C times D, A times D. The concentrations of all of these raised to the power of their coefficients, expressed as a ratio with products over reactants, is Kc. Whew! I think we need to have an example of this. Okay. Let's take example. The Haber process is where we make ammonia from hydrogen gas and nitrogen gas. And there's ammonia, NH3. Notice we have to start with a balanced reaction. There's 3 moles of that, 1 mole of that, 2 moles of that is formed. So now we put the products on top, the numerator, NH3. We raise it to the power of its coefficient, which is 2, divided by, as the denominator, the H and the N, their concentrations, molar concentrations, and you see there's a 3 there and there's a 1 there. So the H is raised to the power of 3, the N is raised to the power of 1, which means you don't have to write the 1, it's understood. Now it says here, as a general rule, the concentrations of pure solids or liquids are included in the equilibrium equation. Are not included. That's cut off. The concentrations of pure solids and liquids are considered to remain constant and therefore do not affect the equilibrium. Only the concentration of gases and solutes in liquids are included. So if you look at these are all gas. Gas goes to form gas. So gases are included. But if we have solids and liquids, we don't include them because, say you've got water, its concentration of water in water is 100%. Say you have sugar, the concentration of sugar is 100% if it's a solid. So you can't say that you've got a concentration of it, it's meaningless. It comes to 1. So you substitute where you have a solid or a liquid, you just say 1 times. Now let's have a look at this. Calcium carbonate, when heated, goes to form calcium oxide and CO2 gas. So you've got a solid goes to form a solid and a gas. The Kc is there just equal to CO2 because both of those are solids. So we leave that out, so that doesn't go at the bottom, that doesn't go at the top, and all we're left with is the CO2. So the Kc for that reaction is just the concentration of CO2. Now, if the Kc is much greater than 1, the equilibrium will be to the right. Why? If you've got a ratio of products to reactants, and you've got 1 lot of product and 1 lot of reactant, the ratio of Kc will be 1. But let's suppose you produce 2 lots of product and 1 lot of reactant. That means you've got a lot of product at equilibrium and only 1 lot. You've got twice as much product as reactant. So you've got 2 upon 1 is 2, high Kc. But what if this was 1 and that was 2? We'd have a low Kc, which would be 1 upon 2, which is a half. And that would mean we got 2 lots of reactants and 1 lot of product only. So what is Kc? It's a measure of how far the reaction, how much product is produced at equilibrium compared to how much reactant is left at equilibrium. Remember, your reactants go to form your products. If all the reactants go to form all the products, then we're going to have a high Kc. If very little product is formed and most of it stays reactants, then we're going to have lots of reactants left and very little product left at Kc. So depending on the ratio at equilibrium, we're going to get a high or a low Kc. So do you understand that? If something has got an awful lot of product, that's what we want. We want to produce it. We want a high Kc if we're making the product. So we want all the reactants to go to form products. And if it's a reversible reaction, we can manipulate the conditions so that we can get it to go in a certain direction. Look here, still on page 210, around about there. Concentration, temperature, pressure, those factors can affect which direction our reaction goes to. So if we add more concentration of reactants, we can push it to the left or the right. We can push, if we've got more reactants, we can make more products. And we can treat heat as a reactant or a product depending on whether it's an exothermic or endothermic reaction. If heat is produced in the reaction, then heat can be regarded as a product. And likewise, pressure can affect which way a reaction goes. Does it go to form more product or more or less product? Now, in this particular soda stream closed system, we had to force gas in. So increasing the pressure of the gas forced it to produce more carbonic acid. So this forced the reaction from left to right. So increasing the pressure will result in more product being formed. But in a closed system, product and reactant are in equilibrium. Their concentrations are not changing. We've already allowed them to settle for a period of time, and now the concentrations of the two reactants and products is not changing, and that ratio of products over reactants is our K. You press the top button. A gas plus a liquid goes to form a solution, an aqueous solution. Right, so let's finish off this video by asking you to find the Kc for the reaction of carbon dioxide plus water going to form carbonic acid. And let's give you a Google quiz on this particular video.